Point an automated scraper at Amazon today, and you will likely hit a wall. A quick terminal curl request might return an initial HTTP 200, but every subsequent call immediately triggers a 2.3 kilobyte HTTP 503 interstitial. It reads, "Sorry, something went wrong on our end." This is a fingerprint-based soft block, not rate limiting. Adding a crawl delay changes nothing, and traditional CSS wrappers fail because the DOM structure they rely on is completely withheld. A common reaction to this fragility is scaling up, handing the extraction task to a massive API-based large language model. But throwing a trillion parameters at a locked door introduces severe latency and cost overheads without actually solving the access problem. This graph shows a long-tail token length distribution for HTML documents across the web. You can see the red context limit line cutting off the vast majority of a complex web page's data. Massive models lose critical extraction signals precisely because they drown in the noise of raw, unparsed HTML. The counterintuitive alternative is running a compact, locally hosted 9 billion parameter model. Instead of relying on massive parameter size to reason its way out of mistakes, this local agent operates within strict action space constraints. Reliable web extraction is not a function of model size, it is a function of architectural constraints. The architecture relies on a React loop, wrapping the local Qwen 3.5 9b model. In this loop, the model never sees raw HTML, and it never writes a single CSS selector. This is achieved through query-aware DOM pruning. Before the language model evaluates the page, an algorithmic pass strips out the rendering boilerplate, style tags, and hidden elements, compressing the noisy document into a high-density representation. The model's exact input observation is simply a clean, numbered list of interactable, visible text elements. When tested on server-rendered pages, this pruned approach allowed the 9b model to extract 32 out of 32 records with 100% precision. On JavaScript-rendered content, the model successfully extracted 34 out of 34 records without requiring any additional fine-tuning. Programmatic DOM pruning paired with a localized React loop outclasses raw HTML parsing by design. The core philosophy is simple. You do not fix language model reliability with prompt engineering. To prevent model hallucinations, you must fix them by deterministically constraining the action space. For example, during early testing, the agent hit a failure state where it re-extracted the exact same page 4 times in a row. The fix was a hard Python rule. Once a page yields 0 new records, the extract tool is algorithmically banned. In another instance, the model wandered back to a home page and began extracting spurious, off-target data. The fix here was gating all navigation and extraction actions behind a strict -scope regex, preventing the model from leaving the target directory. The third failure case involved the model hallucinating references to elements that did not exist in the DOM. We solved this by dynamically rewriting the maximum reference variable at every single step. The limit is mathematically forced to equal the total length of the visible elements minus 1. These guardrails ensure that invalid actions are structurally impossible for the model to omit. The system does not detect mistakes after they happen, it physically prevents the tokens from generating. We enforce these bounds at the sampler level using a generalized Bacchus-Noor form, or GBNF, grammar. A llama's JSON schema format serves as the exact mechanism to translate these bounds into token constraints. However, this creates a severe latency problem. Compiling a JSON schema into a token-level finite state machine over a 248,000-word vocabulary takes roughly 14 seconds. By contrast, it only takes 4 seconds to decode the answer once the machine is built. We cannot cache these compiled indices because our element reference maximum changes on every step. The cache would invalidate instantly. To solve latency, the architecture uses dual-path decoding. On the fast path, the model decodes freely. The raw output is checked against the JSON schema in microseconds. If it passes, the step executes. If the free decode violates the schema, the fast path is rejected. The request reroutes to the strict FSM grammar, forcing the model to generate a valid action. This dual-path system delivers the deterministic reliability of rigid finite state machines while maintaining the low latency of unconstrained free decoding. Every single successful step this agent takes creates data exhaust, automatically appending its actions to a trajectory JSON-L file. Over time, this naturally builds a Phase 5 training set for free, yielding 1,200 rows across 96 distinct hosts. The schema focuses on teaching reasoning, like task graph positioning and evaluating observations, rather than raw markup parsing. But there is a strict post-training warning. Supervised fine-tuning learns lookup constants. Because it imitates a rule-based teacher, it does not learn actual probability distributions. The direct implication here is that the model's self-reported confidence metric, its D-confidence score, will absolutely not calibrate to reality. This scatterplot shows uncalibrated confidence in action. We see a flat trend line where high model confidence correlates with completely randomized extraction success rates. This is dangerous because a false assurance of success disables the system's withholding gates. If empirical success does not scale linearly with model confidence, that metric is mathematically useless. You must delete the confidence variable entirely. When moving to physical deployment of the fine-tuned model, there are strict quantization rules you have to follow. The first hard rule is to never use 4-bit GGUF quantization for these weights. This bar chart compares the extraction success of the formats. At 4-bit quantization, the benchmark success dropped from 32 out of 32 down to 12 out of 32, failing due to premature termination. The required alternative is serving the V4 model in uncompressed BF16 via the MLX backend. Preparing that model introduces pipeline hurdles. Using Unslot Studio on Apple Silicon causes two specific crashes during export. First, the Qwen MTP mixin crashes on a fresh process because it asserts an unpopulated class attribute. You can bypass this completely if you pass the --no MTP flag. Second, Transformers exports the tokenizer class as an internal wrapper called tokenizer's backend. This completely breaks auto-tokenizer when you try to load it. The fix here requires manually opening the tokenizer config.json and changing the class back to Qwen2 tokenizer before serving the model. Deploying reliable autonomous scraping agents is currently an exercise in bypassing upstream framework bugs to secure a deterministic local edge environment.